Hi everyone, my name is Scott Pearse. I'm a software engineer at the National Center for Atmospheric Research in Boulder, Colorado. I'm part of the Vapor team, who develops, I'm not sure if everyone's heard of Vapor, it's another desktop visualization application. And there's this good question that we hear a lot. In a world where we have Visit, ParaView, Blender, Viz 5D, and a whole slew of other visualization tools, what room is there in this visualization world for Vapor? And our answer to that is that domain scientists often need dedicated packages to make their lives easier. The scientists at NCAR spend all their time working on their simulation codes of ocean models, atmospheric models, and 3D visualization is inherently more difficult than 2D visualization. I would assert that it's an order of magnitude more difficult because of the amount of data that you have to filter and the amount of variables that you can show simultaneously. This has an implicit bar to entry for scientists who are already consuming have their lives consumed with their science, and so most scientists are apprehensive about 3D visualization. And so Vapor is a tool that we make dedicated to atmospheric, ocean, and geophysical scientists, and sometimes we dabble into chemistry, heliophysics, and astrophysics, but it's mostly tailored to our scientists doing synoptic scale, mesoscale, microscale, and large eddy simulations at NCAR. Our website is www.vapor.ucar.edu, where you can find how to download it, sample data, and a bunch of YouTube tutorials that will cover everything that I'm not going to have time to get through in this talk. But in addition to that, we have a free tutorial on August 23rd that's going to go into more depth than I do right here. So if you go to our website, vapor.ucar.edu, there will be a registration link, and you can sign up for that, again, August 23rd at 11. And we will also be covering a new Python API that we're introducing in our upcoming release. We're hoping to release 3.7 in a few weeks, where you can do in situ visualization, as has been discussed, I think, already numerous times during the talks today. We're open source, and we have binary installers on our website for OS X, Windows, Ubuntu 18 and up, and CentOS 7. This visualization we're looking at right here is an idealized MOM6 simulation of the Drake Passage, which is the most turbulent, I believe, body of water on the planet. It's between Antarctica and Cape Horn in South America, where the global conveyor belt, which is this train of water that pushes its way through the Earth's oceans once every 1,000 years. If you have a parcel of water and stick it in the Drake Passage, it'll take 1,000 years to traverse the entire planet and end up back in the Drake Passage. The Drake Passage is very important for climate dynamics because it affects the temperature regulation of the conveyor belt. It generates these vortices that we can see in the idealized simulation over here on the left. Those little circles end up forming and traveling across the entire planet, and they are important climatically as well as biologically. Climatically, like I said, for temperature regulation, but also biologically, because these vortices end up picking up coral larvae and plankton, trapping them, and then depositing them at random places in the Earth. And so they're very important for disseminating life and biodiversity for coral reefs and plankton. In fact, they found that plankton and larvae actually evolved their own species while contained within these vortices, traveling across the planet over the course of years. And so this is an idealized simulation of that, kind of called, the scientist likes to call it God's bathtub, and I can kind of see why. And another visualization project we're working on with Vapor is kind of, well, pardon the pun, but it's the big hot topic in Colorado. Fire is everywhere in Colorado. This is a simulation of the East Troublesome Fire, which happened in 2001, which was pretty catastrophic. It lasted for 38 days and almost burned 200,000 acres. And over the course of 3 days, it quadrupled in size, which spurred massive evacuation orders for the towns of Granby, Grand Lake, and surrounding regions, which you can kind of see over here. What we're trying to do with this is create in situ visualizations of these simulations to show to people nearby where they live, to convince them to evacuate, because that was the hard thing. People didn't want to evacuate because it was smoky, but they couldn't see this fire line coming towards their property. And so this is this perspective is Granby looking north, and we're hoping that by showing these kind of close-up perspectives. If people can see my house is right there and the fire line is right there, will they, take the warning and the evacuation orders more seriously? This is a little bit closer for comfort. This is Grand Lake, and you can see the fire line. It's a really low resolution map. I need to increase the resolution, but the town is right here, and you can see the fire line approaching it, and it just barely gets spared. But yeah, that's probably the most proximal, I'd say, the line of fire gets to actual properties. Only 63 buildings were burned, surprisingly, during this 200,000 acre wildfire. And then there's one last view from Estes Park, which was pretty much spared entirely. They just got smoked out for over a month. Let's see. Seems I've lost my cursor. But I don't know, that's probably the least compelling one, so I'll just skip it for now. But yeah, East Troublesome Fire made life pretty miserable for over a month in 2001 if you were living in Colorado. Oh, there it goes, and there's the smoke. Let's see. So yeah, that's the East Troublesome Fire, and it turns out that's just a pilot study. We're going to show people in Grand Lake, Granby, what the simulations are showing and see what the response would be, but it's just a pilot for the big one that happened last December. You guys may have heard of the Marshall Fire that happened on December 31st. Just in the backyard of NCAR, 3 miles away from where I live. This wildfire happened over the course of one day. And it was only 1 day long, and it's the most destructive wildfire in Colorado history, causing $500 million in damages. And here's a picture of it right here. And I just acquired some of the Marshall Fire simulation data earlier today. And so I'm going to try to explore that with you guys. I've just cracked it open. There's a few problems, but that's what we're going to be looking at. And what we're going to be looking for is this thing called an atmospheric rotor. If you guys have heard of a weir, it's a civil engineering device to control water flow. And what happens is the water flows over the top of the weir, plummets down, and then creates a vortex, or also known as a hydraulic jump, that is extremely dangerous for swimmers. You can get stuck in it, and it ends up costing lives every year. But the same phenomenon happens in the atmosphere, too, if you have winds coming over a mountain. That rotor cloud is the same thing as the hydraulic jump over the weir. And so there's a lot of photographs and eyewitness reports of an atmospheric rotor being present directly over the Marshall wildfire. And so that's one of the things that we'll be looking for. What was interesting about this rotor was that here's an example of a rotor cloud. If I go back one slide, you can see that rotor cloud annotated above the vortex. You can see the helicity of this rotor cloud. You can kind of see how it's kind of twisting right here. So just underneath it, we have this rapid vortex of spinning air. It's also extremely dangerous for aircraft. I think in the 80s, a passenger aircraft went down in Boulder because it just flew into this rotor, got hit down, and then back up, and the wind shear just flipped it over pretty much. But in the case of the Marshall Fire, there was no rotor cloud. And so the big question for the scientists is, was there a rotor? And the simulations are indicating yes, but I just got this data. I haven't found it, I don't think, yet. So that's what we're going to try to do right now. So I'm going to launch a source build of Vapor on my own laptop. Vapor 3.6 was released back in February, and there's been a few bugs we've fixed, and so I'm going to run from source for this, for the sake of this demonstration, because it will crash otherwise. But there's also weekly builds up if you prefer something more up to date. So once you do install Vapor, by the way, it'll be on OS X in your applications directory or any typical program files directory on Windows or wherever you choose to install it on Unix systems. So I've launched Vapor by my command line. Otherwise, I would have done so through my icon down here. We have this notice board that has the tutorial information and the registration link. I'm just going to ignore that right now. And here we have the interface. Basically, it's all blank. There's nothing we can do because we haven't loaded data. So the first thing I have to do is go to the File menu. And there's kind of two methods of importing data or getting data into Vapor. There's this data format called the VDC. That's a data format that we develop. And what that is where we take your data and we apply a wavelet transform to it. And generate this series of wavelet coefficients that allow you to look at your data at different levels of compression. You can look at your data at full resolution or partial resolution, and if you have a lot of data, if your grid is very large, you're going to find that vapor can become irresponsive after a while, and exploring data is just a pain. So if that's your case, you can convert your data to VDC, crank down the fidelity, get your colors right, get your opacity maps right, and kind of approximate things, and then crank things up to full fidelity. Make a few tweaks that'll take like a minute or two to register, press play, and then don't touch your computer and let things run. So it's just a way to get a little more interactive. And I can go through that if I have time at the very end. But for this, I'm going to go to my import menu and directly read WRF ARW data. Just navigate to my Marshall fire simulation. There are two components to this simulation. I'm going to start with the fire files. Select all those. Okay, so now we have our domain. This white bounding box is our data domain. If you're using Vapor, you need a mouse. You can try to use a trackpad. I don't recommend it. It's going to make your life miserable. So your left mouse button will rotate the scene. Middle mouse button will traverse. Right mouse button will zoom in and out. And you have your home icon up here to go to your default view, looking down at the z-axis as if you're up in space. But you can see we only have our domain. We have nothing rendered yet. And so Vapor is composed of a set of algorithms that we call renderers. I think the parlance varies depending on your application. But to instantiate a new renderer, I'll click on the New button, and I'll be presented with the list of options that I have. And gosh, it looks like it's getting clipped at the bottom, and I can't move this dialog. So it's clipped, but that's all right. I'm going to start with a volume renderer, but I'll go through what we have here. Wind barbs, just wind vectors. Contours can be basically a cutting plane in 3D space, arbitrarily oriented, where you can pick a variable, draw contours on it, or you can do contours on 2D variables as well. I keep on hearing talk about pathlines and streamlines, same kind of thing here. Vapor's Flow Renderer supports both of those, and I'll be covering that. I think that's how we're going to hunt for our atmospheric rotor at the end of this example. Image renderer is an easy way to get a map into your data set. ISO surfaces, just a single data value along a surface in your 3D field. Models are just STL files. Here we have a windmill with a turbulence, volume rendering behind it, arbitrary oriented cross sections, 2D data, volume, and I think the last one at the very bottom is a wireframe renderer where you can look at how your grid is configured or rendered in Vapor. So I'm just going to double click on volume and get started, because volume is, it's good for clouds and smoke, and we're going to go for smoke. So we've instantiated our volume renderer, and we can see that instance is now populated in this upper left-hand table. This is where each instance will exist. And as we go through, here I'll just instantiate an image renderer as well, just to show you guys how this workflow operates. So you create instances, and whichever renderer is highlighted in this table is going to have its parameters listed down here on the bottom left. And so if I want to edit my volume renderer, here are the parameters for it. The philosophy for Vapor is to make all of our renderers function as close as possible to each other, so that once you learn how to use one renderer, another one will come to you very intuitively. And so the way we've kind of approached this is with these tabs that are more or less universal among renderers. There's a variables tab that lets you control what variables you're looking at with the current renderer. The appearance tab is how that renderer is being colored, and opacity values are being applied to it. And then there's the geometry tab, which controls where in space that renderer is being applied to. So again, variables is what you're rendering, appearance is how it's being rendered, and geometry is where. And all renderers, more or less, have these three tabs that operate in the same way. So to turn on my volume renderer, I'll click this checkbox to enable it. And we can see our first volume rendering, which is pretty fast. And I think we've already talked about ray tracing. I mean, this is pretty fast because every single pixel on my screen is having essentially a laser fired through that screen perpendicularly to it, where we are sampling until we hit a maximum opacity value. And we're hitting that maximum opacity value at the very surface. And so my ray traces don't go very far. I'm not sampling much data. I'm just hitting that top surface, and so it's pretty snappy. Once I apply opacity to it, it's going to slow down because I'm going to be sampling the data through space. My default variable is pH, which I believe is perturbation pressure. I can scroll down and I have like a metadata tab where I can query the attributes that come from my netcdf file, and it's perturbation geopotential, perturbation geopotential, not geopotential height. But one way or the other, it's not interesting. Let's look at the fire variable. So I'll scroll down to that. And once again, we're looking at a fully opaque distribution of my variable. And so to change that, to start filtering this data and look at the actual plume, which is debatable where the plume begins and ends. But to filter it, I'll go to my Appearance tab, and we have this thing called the transfer function. I think there's different terms for this in different applications. We call it the transfer function. And it's basically a histogram of the distribution of my data. Smoke is kind of a funny variable. It's impulse over here by 0, and then the other values are so minuscule that they don't even register as a pixel in the transfer function. So the first thing I'll do is I'll right-click on the transfer function, go to histogram scaling, and choose logarithmic. And we can see a little bit more of a signature over here on the left. And so I'm going to edit the rightmost bound of my histogram and bring it in so we're really just focusing on these values over here. Okay. But that still hasn't done anything to mask out the values that are kind of occluding my vision into the domain. So I have to apply opacity, and I do that with this black bar up here at the top. There's these control points I can click on and just drag them down. And what that's doing is it's applying complete transparency to this data value. The farmost data value you can see is about 0. That's completely transparent, and then I'm ramping up the transparency as we get up to this data point around 0.00016. The color values are being applied to the data values according to this color bar down here, so I can grab this color point, drag it over, and I hope that kind of illustrates the basics of how the transfer function works in terms of color and opacity. There's also some built-in color maps that we can choose from. If I click on this gear icon, I can go to Load Built-in Color Map, and we have 3 different categories of color map. Divergent color maps are pretty good for modal distributions, where you have like a witch hat with a peak in the middle. Typically what you'll do with that is align the, so a divergent color map has 2 endpoints and a center point that converges to white. You'll usually end up aligning that center point with the mode of the distribution and then masking it, applying opacity to the mode so that you're highlighting the 2 ends of the distribution. But this is more of a sequential distribution, so these are the sequential color maps that we offer, and typically when it comes to fire, I start off with this one that's called black body. And let's see, I'll right-click here and reverse that. And that's a start, but since I've been working on fire transfer functions for a little bit, I have one saved. So if I go to this gear icon, I can save my current transfer function. I can also load one from a different session. Actually, fire.tf3. TF3 is the extension that we use for our transfer functions. So yeah, this transfer function was from the East Troublesome Fire, which had a little bit different distribution of smoke, and so I'm going to bring the rightmost bound of my transfer function over like that. And so now we have our smoke over the Marshall Fire. But we don't really know where we are in space, and so for context, we have the image renderer, which gives us maps. So admittedly, there is some weirdness going on with this data set. So when I turn this on by default, my image is going to be drawn all the way up into Nebraska, Wyoming, and Kansas. It really should be only drawn within the data's domain. And you'll also notice that it's extremely coarse. And that's because this is a very highly resolved simulation. If you're looking at something over the continental United States, this image would be more suitable. But since we're so zoomed in, this isn't going to work. And Vapor can only bundle so many or such high resolution maps before it turns into this massive application that's unwieldy and just multiple gigabytes in size. And so the responsibility is on the user then to generate GeoTIFF images. And to do that, my method of choice I would like to show you is this product from NASA called Worldview. Here, let me get out of this. So Worldview is this satellite image server developed by NASA where you can select from a whole litany of different satellite products. If you go to, if you look at this URL, it's a monster, but what you want to go to is worldview.earthdata.nasa.gov. And then from there, you'll be able to add all these different layers. I think the one that I'm using right now is reflectance of Landsat 8 and 9. And it's tricky too, because you have this time slider. You can select your date and time of the satellite imagery. And you're not always going to get the same spot as you're looking for. So the closest I could find is December 28th. The fire happened on the 31st. So this is a few days before the wildfire, which is close enough. But if I zoom out, you can kind of see the satellite swath where it hit, closest to the date of the wildfire. So to create my GeoTIFF image, I'll zoom into my general area, boulders around here. And I can click this camera icon. And I have all these options, the resolution of the image, the file format. It's got to be a GeoTIFF because we need that geospatial information to load into Vapor. And then you just drag this rubber band around where you want. You can click download. Since I've already done it, I'm just going to navigate to my downloaded image. To downloads, and that's the one. And that's roughly what we were looking at a second ago. You can kind of see where the swath got clipped over here on the southeast. So there's our image. It's still a little bit flat though. And so the topography is kind of important in this case, at least. And so in my image renderer, I'll go to the variables tab, and there's a height variable we can pick from. And the canonical height variable in WRF is HGT. I'll pick that, and this should all pop up. I think this simulation in most atmospheric and oceanic simulations are relatively small on the z-axis compared to the x and y. And so what we typically have to do is stretch the z-axis to give more of a, not just a dramatic effect to the three-dimensionality, but more of an observational effect. You can see more if you stretch out that z-axis. And so I'll go to the Scene tab, and the Scene tab contains kind of these global parameters that apply to the entirety of Vapor. I'll go to my Viewpoint tab, and then I can scale it right here, click on 2.5. And now, let's see. We can kind of start to see, or at least I thought I could see earlier, this standing wave pattern, this hump over the fire itself. If I go back to my PowerPoint, I think I remember I pointed it out. There's this rolling pattern to the smoke that the scientists are looking for that indicate the atmospheric rotor. One thing I'm noticing is that my renderings are starting to slow down, and that's because my ray tracing is it's sampling data that I don't really care about. So if I go to my volume renderer and go to my geometry tab, this red bounding box is going to encompass my domain, and it's going to represent the data that is being sampled with my ray tracing. And since we only care about this smoky area right here, I'm going to first turn off the volume rendering to do this a little quickly. I can reduce the region. So if you see as I'm moving these sliders, this red box is shifting in size. And so now we will only be ray tracing within this red box, and all these other pixels will be ignored, and we should be going a little bit faster. Yeah. So I don't know if you can notice that, but that's one trick to use for your volume rendering if you don't care about data throughout the entirety of the scene. One thing a lot of the fire scientists care about is wind barbs. So for my next renderer, I'll click on New, double click. Oh, actually, I can't do that because the meteorological parameters are part of a different data set. So one thing Vapor can do is load multiple data sets at a time and render them simultaneously. So if you have an ocean model, you can render an atmospheric model on top of it if you want to look at the sea-atmosphere interaction, or if your data set has different variables output on different grids, you can load them side by side like what I'm going to do right now. So I'll click on File once again and import more WRF ARW data, and then navigate to my meteorological files. Whoop. Bronco, Marshall, Met. So these are my meteorological files. Bring those in as a new data set. And then I will superimpose a new barb renderer on top of my old data set. And so now that I've imported that new data set, when I create a new renderer, I have this data source. If I only have one data set loaded, I'm only going to be creating renderers on that data set, but now I have two. And it's unfortunately named. They're very similar in name. The F is the fire data set. The one without the F is the meteorological data set. So I'll do the non-fire, the meteorological version. Double-click barbs. And there's my barb instance. I'll turn my volume renderer off for the time being. And now that I go to my barb renderer, by default, we're looking at three-dimensional variables. Vapor defaults to U, V, and W, which are the X, Y, and Z components of the wind field. Fire scientists are mostly concerned with surface winds, though, because that's where the fires are. So I will go to my two-dimensional combo box, where that will default to U10 and V10, which are the X and Y components of wind 10 meters above ground level. And go ahead and turn that on. You can see they're in the middle of space, so what we will do is apply a height variable, HGT, like we did with our image. And you can still, it's still not quite right because we haven't stretched this data set. When I went to the scene tab earlier in viewpoint, we stretched our fire data set. Now we have to do the same thing to our meteorological component. And this is a bug that will be fixed in 3.7, I believe. There's an offset. So one of the things that all the renderers allow you to do is manually position them with the geometry tab. So now that my barb is highlighted, I can go to the geometry tab, scroll down, and we have these transform options where I can translate, scale, and adjust the origin. So I'm going to translate this guy, I believe, 1400. And then we are situated now at ground level. And there are my wind barbs. What I'll do next is go to my Appearance tab, scroll down, and there's all these different options. I'll crank this up all the way to 50. If you ever require more than 50, you can right-click on these sliders, and most of them will allow you to adjust the minimum and maximum value or display the numeric values in different formats, but I guess not right now. I'm going to adjust the link scale because it's kind of crowded, so I'm going to reduce their length and reduce their thickness. And I don't know, personally, I don't think wind barbs should ever have lighting applied to them because, gosh, these are being colored right now, I believe, by temperature. And by applying lighting, we're applying shadows to this. So if we generate a color map, these won't be truly representative of the colors on that color map because of the shadows that are being arbitrarily cast upon them from our two light sources. So I'm going to disable lighting. And now we have something that's more truly representative of this transfer function up here. And so again, we're looking at temperature, but that might not be desirable. Typically, what you want to see colored to your wind barbs is wind speed. And so what Vapor allows you to do is in the Tools menu, you can go to this Python variables option, which allows you to derive new variables based on the variables that currently exist in your data set. So I'll click on New, call it Speed. Then I have to select the variables that I am going to incorporate. Interesting. So my scroll bar is gone. U10 and V10. Oh, you know what happened? Okay, I picked the wrong data set. So this is my fire data set with the F. So I'm going to delete that one, or I'll just create a new one. I'll call it Speed 2. And this will be based off of my meteorological data set without the F. Then scroll down, and there's my U10 and V10 components. My output variable will be speed 2, and the output grid, I'm not going to talk too much about grid staggering. It kind of gets confusing, but Vapor will do its best to pick the optimal grid for your output variable. WRF has like I don't know, half dozen grids that it can be put out onto. And Vapor comes with some utilities that help with this grid staggering problem that I'm going to use right now to make things a lot easier. So to use those tools, I will do from Vapor utils. That's the module that comes with Vapor. I'll import everything, and then I will say speed 2 equals mag, which is one of Vapor's functions that operates on differently staggered grids and brings them onto a cell-centered grid. I will call that on U10 and V10, test it, save it, and now theoretically I should be able to select my new speed variable as my color map variable. I can go back to my Appearance tab, and this is I don't know, I would call this a sequential distribution, so I'll load a sequential color map. I usually, for speed, I think this is one that's called dense or ice, and then bring this down. And that's the basics of the barb renderer, and derived variables as well. Let's turn that off for a second, and I think the next thing I'll cover is the flow renderer, which is probably the flagship renderer in Vapor, also the hardest one to use. I think streamlines and pathlines are computationally expensive, but also there's so many parameters, it's hard to really master them. So I'll start with the simpler one, the streamlines. I'll create a new renderer, double-click flow, and make sure I am using my meteorological data set, which has the wind vectors in it. So double-click flow, and there's my renderer. Turn it on, and by default, I should see a 5x5 grid on X and Y by 1 on Z placed in the middle of my domain. So you can see Flow has a whole bunch more tabs, and that's part of why it's complicated. There's so many more parameters. The big tab you want to concern yourself with is the seeding tab, which controls the initial points upon which we will advect our streamlines and pathlines. Drop-down box letting you select streamlines and pathlines. I'm not going to go into pathlines today. You can control the directionality that you're integrating with, the integration steps, which is kind of like a unitless number that we calculate internally. 100 might be big enough for you, it might not be, you have to play with that one. Vector field multiplier, not too important. Most people have the same units on their wind fields as their data domain, but say your data domain is in kilometers and your wind field is in meters per second, you can use this field multiplier and multiply your wind speeds by 1,000 to get the domain sizes to match up, and turn on periodicity on each axis. The seed distribution settings. Right now we're looking at a gridded set of seeds. If I go down to a 1 by 1 by 1 grid, we have one streamline that's kind of hard to see, but it's right there, placed right in the middle of this red seeding box. Like if you guys remember the geometry tab earlier, we were controlling where we were rendering, what data we were sampling with that. The same thing applies here. You can adjust the extents to which you are rendering your distribution of seeds with this red box. And so my one flow line is now coming out of here. But if I crank this up on Z, you get something like that, and then you can move them around with this red box or with these rake region controllers. I typically use gridded. You can also do a random distribution and a random distribution with bias. If there's a variable that has a high magnitude in a region, you want to see what the flow lines look like coming from that high magnitude region. You can pick that variable and apply a bias weight to it. So let's see, if I want to look at flow lines where pressure is high, this should base them towards the surface. No? There's a lot of pressure there. Well, in theory, that's how it works. And then finally, there's a list of seeds. If you have a text file with a bunch of discrete points that you'd like to render, you can do it that way. Finally, one feature I'll touch on, if you are interested in sampling other values of a variable in a file, or if you're interested in sampling other variables along a flow line, you can pick them from this list down here. So like, let's say I wanted to query temperature along the flow lines as they advect. I could select T, write it to a file, and then if I do that, we now have a sampling, a text file that samples the temperature value along each flow line, along each integration step. So to look for this atmospheric rotor, what I've done in the past is I'm going to turn off the flow renderer, and I'm going to make a column of flow lines in a small region. Let's see. Reduce my Y, reduce my X. Okay, so now I have this more controllable rake region selector. I'll turn it back on. And I have all these flow lines. Let's see. And now I'm just going to start nudging this box. Before I nudge the box, I'm going to go to the Appearance tab, and you can see there's no lighting being applied to the flow lines. I don't know why. I don't like lighting on barbs. I do like it on my flow lines. So I'm going to turn on lighting or 3D geometry. There's some other options I'm not going to touch on quite yet. But to look for this atmospheric rotor, I think I'm just going to come down here and start moving the rake center. Let's move it closer into the front range. So let's move it up on the X. Yeah, there's some craziness happening in there. I'm going to reduce the number of seeds on my Z-axis so it's a little faster. And then I think I will turn on my smoke variable to see where the fire is precisely. Yeah, we're a little bit too far north. Seeding, and then let's go a little further south. And you can kind of see it there. Go a little bit west. So I'm not quite seeing it right now. So what I'm going to do is I'm going to duplicate this render, and I'm going to turn off coloring as well. So I go to my Appearance tab, I use a constant color, and the default is white. And then I'm going to duplicate it. So now I have two copies of my flow renderer. I'm going to turn this one on and apply a different color to it. I'm going to call this one green. Back to my seeding tab, and now I'm going to nudge this one a little bit further north. That looks like. Well, not quite. Yeah, that looks, I don't know, that looks like some vorticity parallel with the front range right there. So that could be something. I mean, the rotors aren't persistent throughout the entire simulation, but they should be stronger at certain time steps in certain regions than others. And so that kind of demonstrates the flow renderer, I suppose, in this context. I guess I'd like to demonstrate some other renderers in a data set that's not so big, a little bit quicker to respond. So I'm going to close out on that, and I'll open up my Vapor version 3.6 from my menu. And again, I'll go up to File, Import, NetCDF, CF data. Again, this is NetCDF data that follows the CF conventions. That just means that it has coordinate variables and a few attributes that describe how the grid exists in space. So this is under data, CF, and this is data from Lee Orff from University of Wisconsin. This is a F5 tornado simulation. So here we have our domain. And I guess the first thing I'll do is demonstrate the slice renderer by instantiating that, turning it on, and then by default we're looking at dBz, which is not bad, but I think vorticity magnitude is his variable of choice. So you can kind of see the vortex right there. What I'm going to do with my slice renderer is go to my Geometry tab, and the way the slice renderer works is that it allows you to rotate on 3 axes and then apply an offset. So if I offset my default XY plane to the very bottom, here you can see the base of the tornado. I'm going to bump that a little bit up. I'm going to duplicate this and then rotate this one along the x-axis, turn it on first, and then offset it and kind of set up kind of like a movie theater. I'll duplicate that and then rotate that along Z. Will that work? Yeah. So you can kind of see how it's rotating in real time right there. And I don't know, that's not the best transfer function. There's not enough contrast between the two ends. But let's see if we just change that to 1. 1. 1. And I'll say that's good enough. And I guess I'd like to demonstrate a few more points on the flow renderer. There are some options that I didn't cover previously. So if I go to my flow renderer, create a new one, go to my seeding tab, and then I will want to distribute my seeds at the very base of this tornado by constraining my box to the bottom, like this. Okay, and I'll do a gridded distribution, just turn that on. By default, it's picking our U, V, and W variables, and then let's see, we'll get that in there right at the tip of the vortex. So there's the streamlines getting advected upwards. And I will cover a few of the appearance parameters, again, how this is being rendered. If I scroll down, we already saw the use constant color field. Renderer types, we have tubes, samples, and this one thing called KGLWTH. I don't know what that stands for, but it's good for showing convergence and divergence. I'll show that in a second. First thing I'll do is turn on 3D geometry, and here we have our lighting being applied. You can do things like change the radius scalar, make her thicker or thinner. You can show the direction with arrows. And different parameters will show up as you enable or disable them. There's this one option to fade the flow tails, which is kind of like faking path lines through streamlines. So I can animate the steady flow like such and change different parameters so that the fade happens over a shorter or longer period. And when the start time starts, it's something you really have to play with to get something that you like at the end. There is no algorithm to follow to get the correct parameterization for this. But yeah, we can do tubes, samples, done as glyphs, circles and arrows. And KLGWTH, which is kind of interesting. I actually saw a news article this morning that I would like to use with KGLWTH. There's this this photograph of a sprite, which is like it's a electric ejection out of the top of a severe thunderstorm, and you can see a lot of convergence down here through going through purple to red, and I feel like KGLWTH might be a good candidate to simulate that. So I'm going to do, oh, that's interesting. So I'm going to go back to tubes, glyph type. Glyph type should not be present. Oh, there it goes. Okay, so there's KGLWTH. Something's funny right now, though. But let's see. I'll go up to my transfer function. I'll try to pick something that is sequentially, I think Kindleman. This might be the, thermal. Might be the color map that most closely matches what we saw in that sprite image, and come down. And what you can see, if I go to my seeding tab, and let's do 15 by 15 on X and Y. I guess the more densely compact these streamlines get, the more their value or luminance gets applied. So the more that the ray traces through these streamlines, the more bright they become. And I don't know, with enough playing, I'm wondering if I can get something that looks like that sprite, but I haven't really gotten there yet. But that's KGLWTH. The more dense the streamlines are, the more bright they are. I think I'm close to the end. I can talk about, well, one thing I can talk about, I can do a demonstration of the compression that we do with the VDC. So if I go to data, and I'm not sure if you guys can see that, data, CF, ORF, may control, test, 24, may control, 1, 2, 1, 2, 4, star, test. Uh-oh, I think that included my zip file, that's why. Well, I'll just do 3 and 4. Or not, let's just do a single file. All right, so if I go to applications, vapor.app, contents, yeah, Mac always puts this really long path. Let's see. before the installation directory. So Mac OS, okay, so if we look over here, we have all these different data conversion tools. We have these VDC create tools, CF VDC create. There should be WRF VDC create. All of these VDC create tools create a metadata file that describe the structure of your grid and all the variables contained within. So we have to create that metadata file first. And this is CF compliant data, so I'm going to do CF VDC create on 24 make control 01, and then execute that. And then I have to give it the file name. This will be test.vdc. And then the corresponding command, the second one we have to run, is the actual wavelet conversion, which is CF2VDC with the number 2. So CF2VDC on the same data input file and targeting the same VDC metadata file will apply the wavelet transform to that single time step. And I think I was doing 0001. I'm just going to create a new session. And then once that's done converting, my footprint, the footprint of the data, the size of the data on disk will have doubled, but I will be able to look at it at different levels of compression. So in this case, I will do file open VDC, go to my selected directory, which is CF, ORF, make control, and test.vdc. I should be able to open this while the conversion is happening. So here I have our domain. Create a new volume rendering so you guys can see the effect of this compression at different levels. And let's see, is DBZ done yet? Yep, okay. So now this is a low fidelity. You can see down here in my data fidelity selector, we have a kind of like a simple controller where you can select low, medium, and high fidelity. Let's go to medium and high, where high is the perfect reconstruction. There are more fine-tuned controls, level of detail and refinement level. These are just parameters used in the wavelet coefficient world. Most people don't have to worry about them. Low, medium, high is sufficient for most. I don't have a timer. I wish I could time the rendering speed for these different parameters, but I can hear my computer start to kick up after being in the high mode. If I duplicate this volume rendering and I do a high one and a low one, and I take my high one and I render it over here, and then I take my low one and I render it over here, we can probably get a side-by-side comparison of what they look like next to each other. So something like that. You can kind of see how the structure of the variable is still kind of there, but you're just going to get much more performance speeds if your grid is huge with the low fidelity rendering. So I guess I can open the floor to questions, or I can keep going. There's more to talk about, and if you'd like to check us out for the tutorial, and we'll be doing more in-depth coverage, as well as going over the scripting API, which is an exciting new feature. At least I think so. Yes.
I've used Vapor in the past, and I remember one of the selling points was supposedly it would work on GPUs. Is that still a selling point? Because I tried to port it to a supercomputer and I couldn't get it to work. And so it's many versions ago. I abandoned it, but I didn't know if that was something that you were.
So Vapor has always needed GPUs 90% of the time. We've integrated the Osprey renderer, which can do CPU rendering. But I wouldn't recommend using Vapor without a GPU. So you were installing it on a cluster, and
I was trying to do it in NAS, in NAS's center, and I couldn't get anywhere. I did it on my local laptop, but I couldn't get my data set down to work with it because it was too small.
So one of the technologies that we have to use on our cluster is called virtual GL, where it's like GLX forwarding between the cluster and your desktop. And so we use a stack that includes a virtual GL on the server, as well as a Turbo VNC or Tiger VNC. Yeah, you have to have those. You can't do X forwarding with OpenGL for it to be performant. So we're using VNC software?
VNC regularly. But yeah, it was a while ago, like several years ago, like in the 2 version.
Were you able to get other 3D graphics applications?
I was able to get some stuff, but I ran into the limit that my domain was too large for what I was trying to do horsepower on my local laptop, and so I ended up having to go to another solution.
Okay. But did you get Visit or ParaView running on your cluster?
No, I was using Vapor.
Okay. Because that would just indicate to me whether the problem is with Vapor or some kind of configuration with the software.
It was just something I was trying. I found it. I thought it was pretty cool. I tried to use it and failed.
Send us an email, because like we have a whole team that deals with this stuff all the time. We've gotten Vapor on Noah's Hera cluster, which is similar in setup, I'm imagining. So, thanks. All right. Well, if there's no more questions, I'll thank you for your time and hope to see you in the tutorial.